Hi everybody, this is Dr. Nigro with a physics notes screencast. This screencast is going to finish up our notes packet for our unit on Newton's first and second law. This screencast is going to focus on some problem solving. Now the problem solving in this unit is not that different than what we've done in the past. You're going to need to read the problems carefully, identify the variables and understand what those units are telling us about those variables, identify what we're looking for, and then use the right formula. So we're going to want to have variable lists, show formulas, and make sure we have units with those answers. All right, so let's start with our first problem. Find the net force acting on an object if its mass is 6 kilograms and its acceleration is 12 meters per second squared. All right, so we have a mass value of 6 kilograms and acceleration value of 12 meters per second squared, and we're asked to find that net force. Okay, so we can actually determine net force in two different ways depending on what the problem gives us. If you're given a free body force diagram or the forces that allow you to draw it, then you're going to add the forces up to determine that net force. The other option is if you're given mass and acceleration, then you're going to utilize Newton's second law to determine what that net force is. All right, and that is the case here. We have mass and acceleration. So that net force is going to be equal to mass times the acceleration. So in this case, 6 kilograms times 12 meters per second squared is going to give us a net force acting on our object of 72 newtons. Okay? So we'll move on to the second one. This one asks about the mass. What is the mass of the object if the net force is 18 newtons and the acceleration is 2 meters per second squared? All right, so again, this time we've got F net is 18 newtons. We've got an acceleration value of 2 meters per second squared, and we're asked to find the mass of that object. All right, we're going to use Newton's second law again. So F net equals mass times acceleration. If we plug our values in, we have 18 newtons is going to be equal to our unknown mass times 2 meters per second squared. So we're going to divide both sides by 2, and we have a mass of 9 kilograms. Okay, one more. This one, of course, is going to look for that third variable. What is the acceleration of an object if the net force is negative 10 newtons and the mass is 5,000 kilograms? All right, so, sorry, not kilograms, grams. So 5,000 grams, we have an acceleration, a net force of negative 10 newtons, and we're asked to find the acceleration. All right, so the first thing we have to do before we solve the problem is we got to fix our unit issue. All right, net force is in the unit of newtons, and newtons is kilograms times meters per second squared. So we have to have our mass in kilograms. All right, so our net force is going to be equal to the mass times acceleration. So in this case, negative 10 newtons is going to be equal to 5 kilograms times our unknown acceleration. So we're going to divide both sides by 5, and we have an acceleration of negative 2 meters per second squared. All right, now remember, acceleration and force are both vector quantities, which means that negative sign is just telling us the direction that that particular variable is being applied. Okay, let's move on to this next one. All right, an object at rest goes into motion covering 22.1 meters over 13.5 seconds. All right, we're then asked what is the acceleration of the object, and then if we're given the mass, what is the net force? Okay, so now the problems are getting a little bit more complicated. We have a little bit more information. All right, if the object's at rest, that means the initial velocity is 0. All right, it's going to cover a distance of 22.1 meters in a time of 13.5 seconds. All right, so with that information, we have enough to calculate the acceleration value here. We're going to use our distance formula. So that initial velocity times time plus 1/2 at squared. Because that initial velocity is 0, that first portion of our formula is going to go away. So we're going to plug in 22.1 meters. That's going to be equal to 1/2 our unknown acceleration times 13.5 seconds squared. All right, so we square that, move our stuff around to solve for that variable, and we find that our acceleration here is 0.24 meters per second squared. All right, now we're going to utilize that acceleration for the second problem. So down here we're given a mass of 150 kilograms, and we already know our acceleration is 0.24 meters per second squared, and the problem asks us to find the net force. So we're going to once again be using Newton's second law, where that net force equals the mass times the acceleration. All right, so in this case, 115 kilograms times 0.24 meters per second squared, we're going to have a net force of around 27.9 newtons, or 28, depending on what you want to do, acting on this object. Okay, so a little bit more complicated than the first three, right, but not too bad. All right, now we're going to move into a problem. It looks like we're going to be drawing a free body force diagram based on this box, but let's see what we have to do first. All right, so we have a cross-country runner accelerating from rest to a speed of 12.2 meters per second in 125 meters. All right. What is the average velocity of the runner? That's going to be our first question. So let's take what we know. All right. We've got an initial velocity of 0. We've got a final velocity of 12.2 meters per second. And we've got a distance of 125 meters. That's what's been given. All right, so we'll start with average velocity. All right, that can either be total distance over total time, but because we don't have time, we can't use that. Or it's the average. So we add the final velocity to the initial and we divide it by 2. So in this case, 12.2 meters per second plus 0 divided by 2, we have an average velocity of 6.1 meters per second. All right. For part B, it says how long did it take the runner to reach her top speed? So now it is asking about time. All right, so we don't really have enough information to use our distance formula here because we don't know acceleration. So instead, we're going to use the average velocity formula again, but this time solve it with distance and time. All right, so we know that average velocity is 6.1 meters per second because we found it up in part A. And we know the distance is 125, 25 meters. So we're going to rearrange and solve this for time. So we're going to multiply t to both sides and then divide by 6.1. And we find that the time is equal to 20.5 seconds. So that is how long it took her to accelerate. All right. Now, what was the acceleration of the runner? All right. Well, we know that acceleration is equal to v final minus the initial over t, and we have all those values. All right, so we plug in 12.2 meters per second minus 0 divided by 20.5 seconds, and we have an acceleration value of around 0.6 meters per second squared. All right, so now we have acceleration. And so then part D asks, were the forces acting upon the runner balanced? All right, so remember, if the forces are balanced, then F net is going to be equal to 0, and there's no acceleration. All right, so in this case, because we've calculated that the runner is accelerating, then we have unbalanced forces. So the answer here is going to be no. All right, forces are unbalanced. All right, because the runner is accelerating. All right, again, if the forces were balanced, there would be no acceleration. We'd be moving at constant velocity. All right, so now we're going to draw a free body force diagram in the box showing the forces that are acting on the runner. All right, so you guys know I like to use boxes for my object. All right, the first thing is we're going to have our vertical forces. The gravitational force is balanced by the normal force. I know this because the object is not moving vertically. It's only moving horizontally. All right, and because I'm a righty, I'm going to have the applied force pointed to the right. All right, so that's the forces that her muscles are providing that are allowing her to move. All right, now it's going to be counteracted partially by the frictional force between her shoes and the pavement, but they're not going to be equal to each other. We know that because we have an acceleration, which means there has to be some sort of net force. All right. So for this last part, if the runner has a mass of 50 kilograms, well, what is that net force? All right. So again, we're going to be using our F net equals mass times acceleration. We'll use our 50 kilogram mass. We'll multiply that by our 0.60 meters per second squared acceleration, and we're going to have a net force of 30 newtons. All right. Now, if I knew how much force her legs could apply, I could then use that applied force and the net force, and I could figure out friction, but we're not going to do that in this problem. Okay. So again, not difficult, nothing really new for us outside of the free body force diagram and that last part. But it's really taking everything that we've learned so far and kind of putting it all together. All right. So we're going to move on to number 6. All right. Number 6 has a car that increases its velocity from 0 to 27 meters per second in 4.5 seconds. It has a net force of 6,600 newtons acting on the car. What is its mass? All right. So let's start with what we know. All right. We have an initial velocity of 0. A final velocity of 27. We have a time of 4.5 seconds, and we have a net force of 6,600 newtons. The question is, what is the mass? All right, so the only formula that we have dealt with so far where mass is involved is either weight or F net. All right, now we can't really deal with weight because we don't know what the weight of the object is. So we can't use that formula. So we're going to have to use the F net formula, which means I need acceleration if I'm going to be able to find the mass. All right, so the first thing I'm going to do is use my other information and my acceleration formula to calculate that acceleration value. All right, so acceleration is equal to V final minus V initial over time. So that's going to be 27 meters per second minus 0 divided by 4.5 seconds. And that's going to give me an acceleration value of 6 meters per second squared. All right, so now that I know acceleration, then I can use Newton's second law and find what that mass value is. All right, so remember that net force is equal to mass times acceleration, which means that mass is going to be equal to that net force divided by the acceleration. All right, so our next net force of 6,600 newtons is going to be divided by 6.0 meters per second squared. So the mass of our object is 1,100 kilograms. All right, so while this problem wasn't scaffolded, it didn't break it into 2 steps for us, we could do this. All right, we understand that the formula that we need to use has 3 variables in it. We were given one of them. We were looking for another, which means there had to have been a way to calculate that third. And in this case, we use our acceleration formula to get that acceleration value that we need for the problem. All right, last problem that we're going to look at. This time we're given a free body force diagram, all right, that illustrates the motion of a car on a highway. All right, so the first question is the car in motion? How do you know? All right, so we look, we have an applied force, and that force is pointed to the right. So if we have an applied force, then we know that the car is in motion. So we would say, yes, there is an applied force to the right. All right, so that means that the car is moving and it is moving to the right. All right, the next question, is the car moving at constant velocity or accelerating? All right, so this is getting at, are those forces acting upon that car balanced or not? All right, and so if we look, we've got equal but opposite forces vertically. So FG and Fn are balanced, all right? But if we look, the applied force is 3,000 newtons to the right. There's a frictional force at 250 to the left, so those are not balanced, all right? So we're going to have changing velocity because the forces are not balanced. All right, so then it comes down to, well, then what is F net? All right, so as we said before, F net can be calculated in 2 different ways. If I have mass and acceleration values, I use Newton's second law. If I have a free body force diagram that's labeled with values, I'm going to use that. All right, so remember, forces to the right are positive, forces to the left are negative. So we're going to have F net equals 3,000 newtons plus negative 250 newtons. All right, so the net force acting on the car is 2,700 newtons. All right. Next, what is the mass of the car? All right, so you might say, well, why can't I just use Newton's second law here? I know the force, but we don't know the acceleration. So there must be a different way to determine the mass. And remember what I said, we can also use the weight, which is Fg. So the mass times gravity is another way to determine that mass. And the free body force diagram tells us what Fg is. All right, so negative 5,000 because that force points down, times our unknown mass, times the acceleration due to gravity, which is negative 10 meters per second squared. All right, so our mass value here is going to be 500 kilograms. All right, so when you're working these problems, if you're given a free body force diagram with Fg labeled, then you can figure out the mass of the object. Particularly if we're on Earth, it's pretty straightforward, just divide by 10. All right, but no matter where you are in the universe, you just divide by the gravitational pull, and that's going to give you that mass. All right, so with that mass, we can now find the acceleration. So we're going to combo our F net and our mass value and use Newton's second law to find this acceleration. So our acceleration is going to be equal to the net force divided by the mass. So in this case, 2,750 newtons divided by 500 kilograms is going to give us an acceleration of 5.5 meters per second squared. All right, so we've done a lot of work so far, but we're not done. All right, now we're going to get into more about the motion. All right, it says if the car covers 250 meters over 9.5 seconds, what is the average velocity? All right, so we've got a distance of 250 meters. We've got a time of 9.5 seconds. And the question is, what is V average? All right, so remember, V average can be equal to distance divided by time. And since we have those values, we're just going to plug them in. 250 meters divided by 9.5 seconds. And we're going to end up with an average velocity of 26.3 meters per second. All right, so that is our average velocity. All right, so we're going to use this along with this last piece of information, all right, that the car was initially at rest to find the final velocity. Now, there are two ways to do this, all right? Method number one, I have V initial equal to 0. All right, I'm looking for V final. And if I look back up here, I actually know what the time is and I know the acceleration. You have to look around to find all the information. All right, but the time is here, the acceleration is here, so I can use my V final equals V initial plus A times t formula and find that final velocity. So this is 0 plus, whoops, not 9.5, sorry, 5.5 meters per second squared times 9.5 seconds. So we're going to get a final velocity here that is equal to 52.3 meters per second. All right, so that is one way to do it. The other way is to use my average velocity formula. I know that's final velocity plus initial divided by 2. So if I plug in 26.3 meters per second, then I'll have V final plus 0 divided by 2. So I'm going to multiply both sides by 2, which gives me a final velocity of 52.3 meters per second. All right, so you can see it's a different method, but we get the exact same answer. All right, so these problems are similar to what we've done in the past. You need to read them carefully. Make sure you list out your variables, identify what you are looking for, and then think about what formulas can help you get there. All right, please be aware of problems where you're given Fg, because Fg will help you find the mass. All right, just remember that Fg equals mass times gravity. That is a very handy formula to remember. Okay? All right, so now you're going to go do your own problem, see how you do, and let me know if you have any questions.